All right, so let's apply Shockley-Reed-Hall to interface states and calculate some relaxation rates. Okay, the point is, in the previous segment, we introduced the concept of surface states. Now, that is, in principle, similar to the recombinations that we had going through trap states, but the math is going to be slightly different, and we'll step through the math, and I try to make it somewhat intuitive with some examples. So hopefully this is not too painful. All right, so let's go after the recombination current. So let's compare this to a single bulk trap. We had an expression for this bulk recombination like this. And here we took out the taus and put in the capture coefficients and the total trap number of traps, okay? Because we're wanting to relate this now to individual traps, not to an overall minority carrier lifetime. So we can bring up the total number of traps up to the numerator like this. And we do this in analogy for these surface states. What we're really doing is replacing the number of traps that is somewhat countable in bulk with a distribution of traps that lives here at the interface. We said there's lots of them, and we assume that for a given delta E, that there's a certain density of traps and a certain energy. You can think of, if it were homogeneously distributed, you might have a D that might just be a constant, or maybe there is some distribution of traps that is mostly in the middle of the gap. So this would be DIT, or DIT of E, some density of interface traps as a function of energy, and you would integrate these to get a concrete number for a given energy range. So that's really equivalent to the number of traps that you are considering here, okay? And in that segment, in a sense, each segment here, each energy segment we consider them almost like independent traps, and there's only going to be, just like this, a single process down. Okay, like this, okay? Again, it's not going to be a cascade down. All right, so in order to then get the final recombination of the system, we need to integrate this rate over the band gap here, okay? So instead of having just a bulk recombination, we have an energy-dependent rate, and we integrate that rate over the energy range of interest, okay? All right. Now, let's consider a donor-doped system, okay? That means we have N, D is large, and that's going to be roughly N0. Okay, so lots of electrons. And we're going to do low-level injections, meaning not tremendously large numbers, but those numbers are still going to be larger than the amount of whole states that we have available at equilibrium. All right, so with these assumptions, let's plug these in. So this should be DIT here. And all we're doing is, again, plugging in N equals N plus delta N. So N0, and the total N is enhanced by a perturbation delta N. And we're doing this in the surface region here, so we're going to consider these numbers with an index S. Okay? So we're repeating everything we did before, but now with a surface density. All right. Now we're doing an approximation here. So remember, just like this, we'll cancel this. And we had this term here is also going to be small. and we're going to be left over with delta P and N, okay? So those are the large quantities. And then on the bottom, again, we're throwing out this delta N compared in this sum here, and we're throwing out this guy here, okay? All right, so, and then you multiply through and collect your terms. All right, so we have an expression for the rate as a function of energy that's to be looking complicated, similar to the original Shockley-Reed-Hall expression, but now for surfaces. All right, let's work with this expression a little bit to make it more intuitive or get some results out. And these results were actually fundamental in the understanding of semiconductors. For that, we'll consider this denominator here in more detail. I'll call it a window function. That's why I call it W. And we can also have NSO equals ND, so we can substitute that in here, okay? So we'll use these two expressions to really modify R and figure out how to do this integral here. That's the goal, okay? So the goal is doing this integral. And we have this integrand that has now the window function here in the denominator. Right, let's turn this graph around and introduce some numbers into this graph. Of course, we have the intrinsic energy level. It's roughly mid-gap. This here is the valence band edge and the conduction band edge. We said we have a donor-focused, donor-doped system. So that means the Fermi level is closer to the conduction band and above the intrinsic energy level. Okay, good. Now, we are needing to integrate this function R over this energy here from EV to EC, okay? This is the integral we're after, from EV to EC. This term here is rather complicated. Has lots of exponentials in it. You'll see it in a minute. My aim in the next few slides is to introduce a windowing function that looks like this, where W is now approximated by 1 between some Fermi level here and some other Fermi level here. It takes on the value of 1, and it's infinite anywhere else. That means you can forget about integrating here and here, and you can change the integral from to be determined EF prime and integrate up to EF. And you just replace this by 1, and you have the numerator to be integrated, which will then be just some density of interface traps, density of states of interface traps, some excitation levels that you might have, and some capture rates. Okay, that's the goal. But how do you get to this approximation? What's the physical insight? And remember, all of this was done in the 50s, where there weren't many computers where you could calculate a lot of these things. Now you can plug them in, some of these expressions into MATLAB and plot it, but these researchers actually struggled with the concepts of how do you represent this, and how do you bring up a formula and expression for this. So this is the early days of understanding this in solid-state devices, and this approximation here has some interesting aspects that are then also important for the fundamental understanding of semiconductors. All right, so let's get us this window function. Let's start out with asking what's the value of this window function at the intrinsic level, okay? We're going to evaluate this window function. We have expressions for N1, P1, S0, and Ni, right? We said it's donor doped, like this. And we had expressions from the previous sections here in this lecture series on the the coefficients N1 and P1 that related the emission to the capture. Okay? So let's evaluate some of these expressions. At EI, it's pretty easy. You plug in EI here. You can evaluate this pretty easily and chuck these numbers in. And NS0 under N doping is 10 to the 8 is ND. So let's put in some numbers. So typical doping could be 10 to the 18. Ni is typically 10 to the 10 in silicon. So you have 10 to the 10 over 10 to the 18 and 10 over 10 to 10 to the 18. I mean, this ratio here will be some number between 1 and 10 or 0.1 and 10. That ratio is not going to be over order of magnitudes, right? So basically, you can forget about these terms. So that means the window function is 1 at E equals EI. For all practical purposes, it's 1. So that's an easy one to calculate. All right, now let's look at this energy EF here. So again, we can plug in EF for the expression of N1. And if we plug into this expression EF here, you see that that is actually the same as NS0, which is 10 to the 18. We know that P1, N1, the product is Ni squared. So law of mass action, therefore we can figure out what P is. Well, 10 to the 20 divided by 10 to the 18 is 100. So again, the product of 10 to the 18 times 10 to the 2 is 10 to the 20 Ni squared. So you can, in practical considerations, forget about this P1s. All right, so let's plug those values in, and we get 1 plus 10 to the 18 over 10 to the 18, this guy here and this guy here, and 100 over 10 to the 18. Again, this is somewhere 1. Either way, it's not going to compensate for 10 to the 16 difference. All right? That means this value is ballpark 2, very close to 2. So we have another point. All right. Those are some values. Now let's take this other expression here for the window function and plug in these expressions. We get something that looks pretty gnarly. And we can divide out the term this guy with this guy, right? Yes. And again, this guy with this guy. There must be a minus sign error here. Oh no, okay. Minus, minus, minus. Okay, plus with minus. Okay, good. And then we have an expression for the window function that now involves energy and Fermi level, and energy, minus energy and Fermi level. Okay, they're sort of symmetric to each other. Okay, so let's just define that little x is beta times E minus EF. Then we have the window function is 1 plus an exponential and plus some coefficient with a negative exponential. All right, so you have an exponential that grows, and it's 1 at EF. That's this term. So it's 1 plus 1. So if you put in an x-axis here, for this one it would be, for this one it would be, if E equal EF, we could set x to 0 right here, okay? All right. This correlates, and we have an expression for this windowing function that kind of looks like 1 plus e to the x, okay? Now, by symmetry, let's look below EI in this section here. We have this term, 1 plus a e to the minus x. Otherwise, with this coefficient a that is ballpark 1, you have an exponential that grows this way. All right? So we pick some EF prime where this term would be 1, or the sum of it would be 2. Let's just define that, okay? We can do that. Let's define the windowing function of EF prime to be 2. That means these terms here that are circled need to be 1. I'll pick any one of those and try to set it to 1 to figure out what the EF prime is. All right, so let me do that. I'll plug in these expressions again, and I'll plug in EF prime as an energy that we're considering. And I get an expression that looks similar to what we've seen before. I had plugged in ND here. And that's an expression by which you could figure out what is this EF prime. And you would get this exponential function as described here. I find this rather unsatisfying and complicated and not insightful. So I would say, let's assume, just for argument's sake, that CPS over CNS is 1, meaning the capture of electrons and the capture of hole, that coefficient is identical. Okay? Just for argument's sake, let's do it. That means we have maybe some correction to EF prime. We'll get some slightly corrected one. Maybe it's bigger, smaller. Let's figure out how large that correction is. But let me plug in EF prime, the approximation tilde, into these expressions here. Okay? Now, if I plug EF prime in here and say that this term is 1, that means I find these guys. They need to be identical. Okay? This is equal to that. Okay, that means my EF prime tilde, the approximate one, is actually a mirror image to the EF I do have. So you give it the doping, you determine what the Fermi level is. If you have very heavy doping, the Fermi level moves up further to higher energies. This EF prime tilde that would set the window function to 2 is the mirror image about the intrinsic energy level. Okay? That I find more intuitive, meaning you see some symmetry in the problem now. So you could see the windowing function should look something like that, symmetric about EI. Okay, now the question is, how different is that quote-unquote true EF prime from the corrected one? So let's do this. Let's assume that we want to determine what is the correction, the delta E, that will give us from the very simple EF prime the quote-unquote true EF prime. So let's plug this in here. Don't assume anymore that the ratio CP over CNS is 1. We get an expression like this. Nothing happened, but we can pull this delta E out in an independent exponential like this. Okay? Actually, it should be. Here's the exponential. Right? Good. So, the rest of the expression is what we already had. EI minus EF is EF minus EI for the tilde. So, NI's cancel, these exponentials cancel. That means CPS over CNS times this correction to the exponent is 1. That means E to the energy correction is the ratio of CPS over CNS. Okay? So how big is that? So we'll just solve it for delta E. KT times log of CP over CN. Okay, so how big is it? Let's assume we know the ratio to be somewhere between 0.1 and 10, just for argument's sake. That the capture of electrons and capture of holes, the ratio between the two varies by a factor of 10. ballpark. Okay? Now, let's plug in 10 that into a log. Natural log is 2.3 times kT. At room temperature, kT is about 25 millielectron volt. That multiplies out to 60 millielectron volt, or 0.06 volt. Now compare this correction, the delta E, to the total gap of silicon, which is 1100 millielectron volts, or 1.1 eV ballpark. So this is a 6% correction. On this picture here that I'm drawing, the lines are separated by each other of 6% of the total graph. So very small. All right. That being said, we can figure out this window function and can introduce this approximation now. Okay, so we know that these exponentials rise here around the Fermi levels at an energy range of kT. Okay, that energy range is 25 millielectron volt. That is how the exponential rises up. Okay, so we're replacing these exponentials by a discrete function, a window function like that. All right, so when we do that, we can actually run this integral and calculate it pretty easily. All right, so now instead of doing the integral from EC to EV over this complicated integrand, we just run the integral from EF prime and EF, where basically they are mirror images of each other compared to the intrinsic level, and calculate this integral. All right. Now you might ask, well, there's some fudging here and all that, but the fudging gets worse. So we're ready to evaluate this integral, but we'll take a small critical insight detour, and then we'll evaluate it. Okay. So what's the small detour? In these discussions, in this derivation, we looked at these surface states that we assume to be distributed throughout the gap. We derived a windowing function that meant that any trap that is inside this energy range here is going to help recombine electrons into with holes. Okay? So now the insight here is that only roughly mid-gap traps act as recombination centers, right? You have to be inside the window of EF. Now the question is, donors are also like traps. All of this mechanics that we've done here is valid really for any traps if we account for them in terms of energy in some delta function. Instead of giving it, we could have done the math for individual traps and their density throughout a semiconductor. But we have a lot of intentional donors introduced. And those donors are not a few. 10 to the 18 are typical number of donors. That gives us the number of electrons in the system. But these donors are shallow. They're a few kT under the conduction band edge. Oh, 36 millielectron volt for silicon is the ground state of the donor. So that means these donors do not act as recombination centers. Because if they did, we could never hold electrons in there. We could not get electrons to go up. They would just then go back down. But due to this windowing function here that governs the trap-assisted recombination, there is no recombination through donors. And that, by extent, is similar for the acceptors as well. Okay? So, by the mere luck, if you will, or smart picking, we have acceptors and donors that allow us to put electrons and holes into the conduction and the valence bands but they don't serve as recombination centers. That's a pretty critical insight to have and to understand in the overall physics. Donors are particular kinds of traps that are close to the conduction band edge. Acceptors are a particular kind of traps that are close to the valence band edge. Their nature is just like any other trap that might be mid-gap, but only the mid-gap level traps are serving as recombination centers. So that's a pretty critical insight to have. So you might say these approximations of, well, here like a square function, why can't we plug this into an algorithm and do these integrals explicitly? They're pretty crude. Remember, there was no handheld calculators even in the 1950s. Okay, so the work was done purely analytic, and actually it gave real insight by thinking about the problem. So that's something not to be dismissed. All right. So now let's go back to this integral and really evaluate it for minority carriers. Okay, so what does DIT look like? And I said there will be more surprises and interest. I mean, if we bickered around the details of what this windowing function looks like, whether this EF is actually moved away by some delta E. Now, compare that to how well we actually know these interface traps. Kind of all over the place, interestingly enough. You can measure them. People struggle really hard to do careful measurements of the energy levels of these density of states and characterize how many states there are in a certain energy range. These are not simple experiments to conduct. And here from the textbook, here's this plot. You can see there's a lot of data all over the place. Ballpark, the density of states of interface traps in a clean material for this in silicon is around 10 to the 10. All right? The numbers go up to 10 to the 11 and maybe ballpark, what is this, 2 times 10 to the 9. Okay? So ideally, of course, you like to, in most cases, you like to have the density of interface traps to be low. But imagine now whether your windowing function goes like this or is really square. The best you can do in a system like that is actually assume it to be constant. Okay? And then your correction here that you do are small compared to what you don't do by assuming a real distribution. Okay? So, that being said, this correction we computed just shows you can do it, and it's kind of cute math, but in the big sense of approximations that are being made to understand the system, going with good approximations. All right, so if that's the case, we pull out DIT outside of the integral, then it's uniformly distributed, and we get basically an EF minus EF prime. And that's the recombination rate times some capture coefficients times some density of states, interface trap, times the number of extra carriers. And that all of that stuff here is multiplied together into something called the surface recombination velocity. So it's a parameter that people measure, and it's an experimental fitting that is being done with careful measurements. In industry, it's really a quality of surface and process. How good is your process for the semiconductor? And it's really process control. That's why these surface states, you want to keep them low in MOS devices. It's a matter of process control to make sure the production works well and there's no contaminations, there is no variety in the process. Remember, we have 2 billion transistors in these devices, right? Controlling this is going to be essential. But now if you imagine you're working in research, you're looking at different materials, new materials, you actually have to count the dangling bonds. You have to go in the lab and measure it. And this is a beautiful plot here of gallium arsenide with dangling bonds on the top, taken again nanohub crystal viewer, and you counted the dangling bonds, etc. This seems like an academic exercise, but if you're working in a structure like this, for example, here taken from Wikipedia, where there's silicene that is being grown in experiments, people do electrical measurements, that stuff is not clean. So cleaning up this process, understanding surfaces, understanding edge states, etc., is the component of research. So you need to understand the fundamentals of these recombination centers and the fundamentals of these rates. So if you work in industry, it's for quality control, speaking the language. If you're working in research and making new materials, new devices, it's speaking the right language with technicians at measurement that measure devices, or you in the lab measuring your own device. So that being said, this is rather relevant, and we talked about the Shockley-Reed Hall for interfaces, and in the next section we're going to calculate some rates, and I'll see you in the next section. Thank you.